The standard procedure for an equilibrium calculation problem is to set up an ice table and use the concept of equilibrium constant to set up an equation. Let's read the problem together. Calculate the equilibrium concentration of nitrogen, oxygen, and nitrogen monoxide present when a mixture that was initially 0.10 molarity in nitrogen and 0.086 molarity in oxygen comes to equilibrium at 600 degrees Celsius. For this particular reaction, it has two reactants and one product. In the ice table, we need to set up a column for each reactant. We also need to set up a column for each product. Therefore, we should have 3 columns for all the chemicals in this problem. We are provided the molarity. Therefore, we need to create 3 rows to represent the concentrations. This is the ice table for this problem. Initial concentration, change in concentration, and equilibrium concentration. You may have already noticed the first letter of the 3 rows are I, C, E. That's why this table is called an ice table. Let's fill the table with the information provided. Next, we need to figure out what kind of change of the reactant and of the product. The initial concentration of the product is 0. Therefore, the reaction quotient is equal to 0. And the reaction quotient is smaller than the equilibrium constant, Kc. If the reaction quotient is smaller than the equilibrium constant, Kc, the reaction will go towards the products, which means the concentration of the product will increase because the coefficient of the product, nitrogen monoxide, is 2. So, we will assume the change in concentration of nitrogen monoxide is 2x. The coefficient of nitrogen gas and the coefficient of oxygen gas are 1. They are reactants. Therefore, they will decrease. Negative tells us that the concentration of both reactants will decrease. And the decrease is x because the Mohs ratio from the balanced chemical equation between nitrogen monoxide and oxygen gas is 2-to-1 ratio. If the change of nitrogen monoxide is 2x, the change of oxygen gas must be x. And nitrogen monoxide will increase, and oxygen gas will decrease. The equilibrium concentration is always equal to the sum of the initial concentration and the change in concentration. I put down 3 question marks to tell me that the equilibrium concentrations of both reactants and the product is what we are looking for. We are not looking for x. Next, we are going to use the concept of equilibrium constant to set up an equation. This is the equilibrium constant expression from this chemical equation. And we already know the value of the equilibrium constant Kc, which is 3.3 times 10 to the negative 10 power. In chemistry, we're done. All we need to do is we use the mathematical skills to find the answer for x. Then we plug x back into the formulas for the equilibrium concentrations of the reactants and the product. Now I'm going to use this as an example to show you how to solve this problem mathematically. From this equation, we can see that the denominator must be much, much larger than the numerator because this ratio is a very, very small number. From this equation, not very rigorously speaking, we can see that 0.10 minus x must be much, much larger than 2x, and 0.086 minus x must be also much, much larger than 2x. Then we can combine the x terms. As we know, 3x is larger than x. Therefore, 0.10 must be much larger than x. Follow the same principle. 0.086 must be much larger than x. As we can see here. At this point, you may wonder, Dr. H, when can we assume x much smaller than the original concentrations of the reactants? As a general criteria, this may not be 100% be correct if the ratio between the equilibrium constant and the smaller concentration of the reactants is smaller than 10 to the negative 3. We can assume that x is much smaller than the original concentrations of the reactants. If x is much smaller than 0.10 and x is much smaller than 0.086, we can simplify this equation to this form. As we can see here, it is a lot easier to find x with this equation than with this equation. To be sure our assumption is valid, I suggest you to finish your calculation and then compare to the original concentrations of the reactants and say if our assumption is really valid. Because the equilibrium concentration cannot be negative, so I only take the positive root. Now I'm going to plug the value of x to these formulas to find out the equilibrium concentrations of the reactants and the products. From our calculation, x is indeed much smaller than 0.10 and x is indeed much smaller than 0.086, which means that our assumption is correct.